our next section, we're going to look at the Internet Protocol version 6 or IPv6, where the previous version we looked at, which is version 4, the main limitation of it is that we're essentially out of address space. So at this point, pretty much every block of address space has been allocated for IPv4. So if you're trying to get a public connection to the internet, it's very difficult to get an allocation from the IANA or from any of the bodies that do the allocation of addresses. Where in the case of IPv4, it's a 32-bit address, or it's a 4-byte value, which means that we have a maximum of about 4 billion addresses. Where IPv6 is an 128-bit value, which is just this insanely large value of possible addresses. So I'm not even sure if there's a name for whatever this address is. It's basically infinite for our purposes, that we can have every device connected and have a public IPv6 address. Now there have been some kind of temporary band-aids for IPv4 that we'll talk about later, like the network address translation or NAT feature that can be used to save some of the address space. But in the case of IPv6, there's more than enough basically for every device to be allocated an address. So not only like your end machines, like your laptop, but also like your phones and whatever other devices are going to be running IP routing in the future. Now when we look at the differences between the format and the addressing, usually this is where it starts to get complicated for a lot of people, especially when you're first learning this. And the key to remember is that when we look at our OSI model, that at the physical layer, at layer 1, we know we have like our copper cabling or the fiber cabling, whatever the physical functions of the network are. At layer 2, we have our protocols like Ethernet or PPP or frame relay. At layer 3, this is where IP version 4 and IP version 6 are going to sit. Above this, at the transport layer, this is typically where we have protocols like TCP or UDP that are eventually servicing the application, like web browsing or maybe voice over IP or mail, like the simple mail transfer protocol. The thing that makes it easier, since we're dealing with this layered model, is when we're using IPv4 versus IPv6, it means that it's only a change in the network layer. So this is only a change at layer 3. All of the upper layer protocols are going to stay the same. So any application that's using TCP for transport, like web browsing, or any application that's using UDP transport, like a phone call, they don't really care whether they're using an IP version 4 packet or an IP version 6 packet for the layer 3 transit. Really the only people that care about this are the layer 3 routers that are in the network. So it's not up to the application really to choose, do you use IPv4 or IPv6. As long as the end host is enabled with an IPv6 address, the application can then send the packets down to TCP, and TCP can choose, am I going to use version 4 or am I going to use version 6? So the key is that nothing is changing here at layer 4 and above. It's only a layer 3 change in the network layer. So when we look at the differences in the addressing format, we talked about the version 4 addresses that use the dotted decimal format, where each of these values is going to be 1 byte or 8 bits. So it's a 4-byte long address or a 32-bit address, where each of these places is denoted by 1 byte. The problem with IPv6 is that the address is so long in 128-bit format, a lot of times it's difficult to denote this. So this is going to be using hexadecimal formatting, where 2 of these characters is going to be 1 byte. It means that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 bytes long. Where typically half of the address is going to be used for the network portion, and half of the address is going to be used for the host portion. Where just like in IPv4, your network portion would be like the street that you live on, and your host portion would be your house number. So it has the same type of hierarchy that when the IP routers are looking at the address, really they only care about the network portion. This is where your routing protocols would make your decision on. then once the traffic gets to the device connected to the LAN, like your default gateway, it's the device that cares about the host address. So a lot of times the way that you will see this denoted, or the way that you'll see it listed, is that the address is going to be some value that normally starts with a 2000, like a 2001, because this is where the first allocation of public addresses are coming from IPv6. So it's going to start with 2001. You're going to have a colon. Then it's going to be followed by a number of different hex values that are going to list what the network is. So this is all part of the network address. If this were the actual subnet, or the actual network, the way that you denote this is at the end you put 2 colons, followed by a slash, and then the prefix length. Like in the case of an IPv4 address, we may have something like 192.168.0.0/24. In IPv6, most of the time the network is going to be a /64. So we have 64 bits that are denoting the network. The rest of the other 64 bits are going to be for the host address. And what these 2 colons mean is that everything else after that is a 0. So we'll look at a couple examples of more specifically how the addresses are allocated and how we use these colons to list them. But just like IPv4, IPv6 is an open standards-based protocol. It means that there's different RFCs that are going to define specifically how it works. And the main one that we're concerned about is 2373, which is the addressing architecture. This tells you how the addresses should be represented in IPv6 as opposed to IPv4. And if we look at the specifics here, there's a couple different subcategories, where the first one is the aggregatable global unicast addresses, or basically the global addresses. These are the ones that we would be using for our internet routing. This would be like public address space that's assigned to you from your ISP. And this essentially is going to be any address that starts with 001 in binary. If we were to look at this from the actual notation of the bits, the first portion of the address, so each of these places between the colons, each of these are 4 bytes. So 4444, 4444, where this is the network, this is the host. Between each of these colons, it's going to be it's not 4 bytes, it's 2 bytes. There's 4 digits, but the digits in hex, 2 of them equal 1 byte. So there's 4 values, but these result in 2 bytes. So that's 1 byte, this is 1 byte. This means that when you read this in binary, there's going to be 16 possible values. So 0000, or not 16 possible values, but 16 bit places, I should say. So this is how it's going to look in binary, that it's 2 bytes for each of these divisions. It says that the global unicast addresses are going to start with 001. So in binary, we're going to have 001. This means that the address could start from 0010, 0000, 0000, and go as far as 0011. Then all of these would be 1s. Where when we look at this in hex, if both of these bits are set, that's going to be what? Actually, it is, no, it's twice this. It's going to be, let me start over. Now I'm confusing myself. This is what the problem with the addresses are. They're too big. So we have the four values. Let's say they're A, B, C, and D. Okay, each of these are 4 bits long. The range is going to start at 0, 0, 1. And it's going to go to 0, 0, 1, and then all ones. We're grouping these together as 4s because this is relating to one value in hex. If this is all set to 1s, the result of this in hex is F. So it means that your address goes from the first one here, which is going to be a 2. Because the way that you read this is, in binary, you have a 1, a 2, a 4, and an 8. If the bit values are 0, 0, 1, 0, this is going to equal a 2. So if you were to look at this in hex, the global range starts at 2, 0, 0, 0. Then it's going to go from that to 0, 0, 1, 1, where here this is a 3. So it means any address that is in this range, this is what is currently being publicly allocated. Where in reality, right now they're giving out the addresses that start with 2001. But this is the equivalent of the public address space inside of IPv4. Where we'll talk about this in more detail when we get to network address translation. But in the case of IPv4, we pull out some addresses like the 10 network, the 172.16.31, and the 192.168. Those are the private addresses. In the case of IPv6, there's a type of equivalent for that, but it doesn't even really matter because this range is so gigantic to begin with. Because if the range is going to be that only 3 of these bits are reserved, if we were to look at the actual calculation of this, it means that we would have 2 to the 125 for combinations. And it's some insanely huge value. So out of the current public addresses, this is how many you could make out of this range of 2000 to 3 FFF. So it's essentially more than you would ever possibly need. But the key is that this is the first thing that the RFC says, that we're going to break it into a couple different portions where these global unicast addresses start with the 0, 0, 1. Then there's some other addresses that we define like link local addresses or site local addresses or multicast. Some of these have equivalents of the IPv4 counterparts, where the global addresses, these are just your public ones. So anything that starts at 2000 and goes to 3 FFF. Then the unique local, these start with FC. This would be the equivalent of the 10 network, the 172.16 to 172.31, 255, and the 192.168.00 through 192.168, 255, 255. So this is like the private addressing for IPv6, which is unique local. It used to be called site local, but then they got rid of these. So now anything that starts with FC00, it's basically for whatever use that you want to use. It's not going to be publicly routable on the internet. Then we have what is known as the link local. The link local addresses are equivalent to the IPv4 addresses 169.254. And you've probably seen this address before because this is what Windows chooses by default if it can't get an address from DHCP. Where the idea behind this is that if you just choose a random number in here, it's probably likely that no one has already automatically assigned that value on the LAN. And you could technically run IP without having a DHCP server then. You wouldn't be able to route your traffic to the internet, but at least the devices locally would be able to talk to each other. because they're choosing this address that's only locally significant to the link or to like the VLAN. But IPv6 is going to have some special uses for these. These are the ones that start as FE80. And if you look at your Windows machine, or if you look at like your Mac OS machine, assuming that you're running one of the later versions of the OS, when you look at the ipconfig/all, you'll see that it's going to choose some of these addresses. Where here, it says that I have a tunnel adapter. We'll talk about exactly what this means in a little bit. But it shows a link local address that starts with FE80. This is going to be just for communication on someone who's on my LAN segment, where normally it's going to be used for me to figure out who are the routers on the segment. And we'll talk about specifically how they do that. But then the IPv6 public address that it chose was something in 2001, because that's part of the global unicast address space, or basically the public addresses. So this one is only for communication on the LAN. This one would be if I were to route my traffic to the internet. So out of this address, this would be the network. So my subnet here that it's automatically choosing is basically 2010004137 9E76. Then this is my host address, CBF, CD8, 52, F5, etc. But this is my network, this /64 that it was choosing. We then also have multicast addresses. This would be used for like your routing protocols to communicate with each other, or if you're using some multicast application like maybe streaming video or some sort of streaming audio. These addresses here would be the equivalent of the 224.0.0.0 to the 239.255.255.255. This is anything that starts with FF, where in IPv4 addressing, these are considered class Ds. In IPv6, there's no classes, and there's no classful or classless routing. It's just regular routing. So multicast is FF. FE80 is local on your segment. This range here is going to be the public addresses. Now, one of the big features of IPv6 that's different of IPv4 is that since the addresses are so big to begin with, one of the things that we can do is have the end host try to automatically figure out what's their host address supposed to be. So like your Windows machine or Mac OS, when you look at the details of IPv6 and you try to change like your network properties, most of them don't even have the option to statically set an address, because there's a procedure that's built into IPv6 that says you're supposed to automatically figure it out based on your Ethernet MAC address. Because at layer 2 Ethernet, we're already assuming that the MAC address is unique, because when the vendor creates it, they're supposed to give it a unique value. So if we take that address and then turn it into a host address for IPv6, we should always end up to be unique on the LAN segment. Then you take that and you put it together with your unique subnet, and you end up with a unique global address. So most of the time when this eventually starts to become popular, because really nowadays we're still not even really using IPv6 that much, but eventually you're going to have an application like DNS that is going to resolve your IPv6 address to a host name, because it's going to be nearly impossible to keep track of what are the actual IPv6 addresses. It's really only the routers that are going to care about that. So this is what is known as the EUI-64 addressing. And the idea behind this is that we're going to take our MAC address of the LAN and turn this into a host address for IPv6. The problem with this, though, is that the MAC address is only 48 bits long, or it's only 6 bytes long. But the host address in IPv6 is 64 bits, or it's 8 bytes long. So we need to come up with the difference between the two. And the way that we do this is by adding 2 extra bytes of padding or just basically 2 extra random bytes in the middle. And it's defined by what's known as this modified EUI-64 formatting. So this is part of the standard. The standard basically says that your host address has to be /64, and your subnet has to be /64 as well. So in the case of IPv4, you could have like a /24 or a /25, /28. IPv6 says you're not supposed to do that. The longest you're going to go is /64. That's your LAN segment. So the way that it does this, it needs to figure out what are the extra 16 bits. It takes your MAC address, and in this case, let's say the MAC address is 1234567891012, and it's going to take the 7th most significant bit, where the 7th most significant bit, if we were to write this out, if the MAC address is 1234567891012, each of these 2 groupings is 1 byte, because the MAC address as well is in hex, just like the IPv6 address is. So this 1 byte is made up of 8 bits, where the first value would be 0001, the second value would be 0010, because this is a 1, this is a 2. I now take the 7th most significant bit, where this is significant bit 1, 2, 3, 4, 5, 6, 7, and I change this. If it's a 1, I set it to a 0. If it's a 0, I set it to a 1. So you're inverting that bit. The result of this here is 103456789012. And the reason why is that this bit inside the MAC address is a special value. It's called the unique local address. It means if it's a unique address, it was set by the vendor who produced the card. If it's a local address, you changed it. So by inverting this bit, you're saying that it's no longer one that was hardware assigned, it's one that we're manually changing. So you invert the 7th most significant bit, and then in the middle of this, you stick FFFE. So right between the 6 and the 7 here in the middle. So the result then would be 103456 FFFE 789012. We can now take this and then add these 64 bits onto whatever our network address is, and that's going to give you the full IPv6 address. Now you can see this on the routers if you were to assign an address, and we were to say at the interface level, IPv6 address, so it's the same type of syntax as IPv4 is, IPv6 address, and let's say I give it the address 2001 AAAA BBBB CCCC, where this is 64 bits long, so this is going to be my network address, :/64, and I want to derive the host address through the EUI-64 format. So it's basically telling the router, this is your subnet, figure out your own host address. If we look at and I configure this on Fast Ethernet 0/0 of router 1. If we were now to look at the show interface, Fast Ethernet 0/0, I now need to take this address and convert it to that EUI-64 format. Now technically I don't have to, the router is going to do it. It's going to happen automatically. But if we were to look at this, we have the value that the MAC address came from. We're going to take the 7th most significant bit, where if these are all zeros, that's what these first two digits are. We're changing the 7th most significant one, and we're inverting it. So now that becomes a 1. The result of this would be 02, exactly. 0211, BBA4 BC20. Then in the middle, we stick FFFE. This should now be the host address that the router figured out. So if we look at the show IPv6 interface instead of show IP interface, the configuration syntax is going to be similar, except most of the time you just replace IP with the keyword IPv6. So show IPv6 interface, it says my global unicast address is 2001 AAAA BBBB CCCC 211 BBFF FEA4 BC20, which is what we figured it would be. So the idea behind this is that, again, since your MAC address is already unique, and you're not really going to care what your host address is anyways, because you're going to use most likely DNS to keep track of it, then just figure it out automatically. And this is what your end host is going to do. If your phone is running IPv6 or your laptop or desktop, it's always going to choose the last 64 bits based on the MAC address. Now, there's a couple other things we need to figure out how they're going to be treated differently in IPv6 basic operation on the LAN versus IPv4. And the biggest change is going to be with the introduction of what is known as ICMP version 6 neighbor discovery, or what's simply known as ICMP ND, where ICMP is the Internet Control Messaging Protocol. This is what we were using for like our pings. ICMP is a suite of management techniques. In the case of IP version 6, one of them happens to replace the address resolution protocol that we previously used for IPv4 over Ethernet, where ARP was used in IPv4 for what? To do your IP address to your MAC address binding. So when you send a packet, an IP packet over the LAN, I need to tell the layer 2 switches what's the MAC address that you're trying to go to. And this is what ICMP v6 neighbor discovery does. It's going to replace ARP, because technically for IPv4, ARP was an afterthought, because IP came out before Ethernet did. So IP was extended to run over Ethernet. In this case, IPv6 was natively written with Ethernet in mind. So this protocol, ICMP v6 neighbor discovery, is always part of the IPv6 stack. Now, the idea behind this is that we're going to replace the ARP with 4 different types of communication. The 2 major categories are called solicitations and advertisements, where solicitation, you're asking for something, and then advertisement, you're responding. The 4 major types are the neighbor solicitation, or the NS. This is basically the same as an ARP request. So I'm asking the neighbor, what is your MAC address? The neighbor advertisement is the reply. This is the neighbor saying, this is my MAC address. We then have 2 additional key ones that are just for the routers. It is the router solicitation, asking who is the router on the LAN, and the router advertisement, where the router is replying saying, I am the router on the LAN. And what this is going to allow us to do is automatically figure out who is the router on the segment, ask them, what is my subnet address supposed to be, automatically figure out my host address based on the MAC address conversion, default my traffic to them, and then automatically get onto the network. So the idea is that IPv6 was designed to be basically plug and play from the end host. As long as you turn the protocol on, you'll automatically find the routers, automatically assign your address, and then be able to send traffic out into the network. Once you do that, then you could run like DHCP version 6, or you could run DNS version 6 in order to do more specific management, but you technically don't have to do this. You could just let the network figure itself out, and it's going to do this based on the ICMP v6 neighbor discovery. Now, since we're going to automatically figure out our addresses, there's one other thing that we need to make sure that doesn't happen, is that we don't choose the same address that someone else has. And this is part of the ICMPv6 neighbor discovery. And it uses an address, a special address that is called the solicited node multicast. The solicited node multicast uses this specific format plus the 24 bits on the end. Now what this format is, it doesn't really matter. You don't need to memorize this. Just behind the scenes, this is the address that was allocated to serve this function. And this special address is used for what's known as duplicate address detection, or DAD. The idea is that if we're going to automatically choose our addresses, we should probably make sure that no one else did the same thing. So even though it's very, very statistically improbable that we would get the same ones, it's still possible that it could happen. So you want to make sure it doesn't happen. And this is what the DAD process does. It says that when I get onto the LAN, I'm going to start sending out neighbor advertisements, telling everyone this is the address that I want to choose. And the way that I do this is I send it to the all host address of FF02::1. This is basically the same as the all host broadcast address. So technically there's no broadcast addresses in IPv6, but it ends up to be the same result. That you can talk to everyone on the LAN if you send the packet to FF02::1. Once you do this, if no one sends you a reply saying that your address is not unique, so if no one sends the reply, I'm going to assume that this is my address, and then I'm going to announce it to everyone. And I'm doing this with the neighbor advertisement. So let's look at a basic example of this, where in the current topology, we have router 5 and router 1 on the LAN. On router 1, this is a sub-interface. This is .2, then I'm going to be configuring this. And before we make these changes, there's a couple of debug outputs that we're going to look at. One of them is the debug IPv6 packets and the debug ICMP debug IPv6 debug IPv6 ND. So these two outputs, debug IPv6 packet and debug IPv6 ND. This is going to show us the process that 1 and 5 are going to go through when they try to automatically assign their addresses. So both on router 1 and router 5, debug IPv6 packet, debug IPv6 ND. On the LAN interface, I'm simply going to say IPv6 enable. That's just turning the process on. And once I do this, we'll see it's going to generate a lot of debug outputs. IPv6 enable. So I'm not manually assigning an address, I'm just turning the process on. And let's look at what the result of this is. Router 5 says that once I turn the process on, I'm sending an ICMPv6 neighbor discovery, neighbor solicitation for the address FE80, then these addresses afterwards, the 211, blah, 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 this is the host address. The destination of this is the solicited node multicast. So this is that special format that they're using, which is here. This is router 5 trying to figure out, if I choose this as my address, does anybody else have it? So it's going to this solicited node multicast address saying, does anyone else have this? I'm asking them, I'm soliciting this. Eventually, it figures out no one replied, because for a neighbor solicitation, the response for this should be a neighbor advertisement. So the solicitation is the request, the advertisement is the response. It didn't get the response within whatever time it's waiting, So it says duplicate address detection said this address is unique. So no one said that they had this. And this format here, FE80, this is specific to what? The link local addresses. So anything that starts with FE80, this is the link local address. For every host that runs IPv6, you're required to have one of these on every single interface. So any interface that has an IPv6 address is automatically going to have a link local one. It doesn't necessarily have to have a global address, but it has to have this one. So as soon as I started the process, the only thing I said at the interface was turn IPv6 on. This tells the router to automatically choose a link local address, so it starts with FE80, and choose the host address based on your MAC address. Where if I was to work backwards of this, if I were to delete FFFE out of the middle, then the 7th most significant bit, if I were to invert this again, the result of this would be 001121C9 0861. This should be the MAC address of router 5's fast Ethernet 0/1. So if I show interface fast Ethernet 01, 001121C9 0861. So you can see that value is encoded inside of here. So it's choosing the host address automatically, but the network address is FE80. This is the link local ones. So eventually, the router figures out this address is unique that I automatically chose. I'm then going to tell everyone this is my address, and I'm going to tell them inside the advertisement also what's my MAC address. So I'm automatically populating their equivalent of the ARP cache for them, what we call the IPv6 neighbor table. So if we look at the output of show IPv6 neighbors, this is the equivalent of the show ARP command. That you're trying to figure out for the IPv6 addresses, what are the MAC addresses that correspond. On router 5, if we look at the show IPv6 interfaces, it says that IPv6 is on this link. It's enabled, but there's no global address configured because I didn't manually set it. The only thing I did was turn the process on. There's also a couple addresses that have been joined that are group addresses. These ones are significant because they're what? FF means multicast for IPv6. FF02::1, that's the equivalent of 255, 255, 255, 255. So it's basically saying I'm a device running IPv6, so I have to listen for this. This one is the equivalent of the address 224.0.0.2. This is all routers. So the router is always listening for, in IPv4, 224.0.0.2. In IPv6, it's FF02::2. This is how people can address all of the routers at the same time. This one here, this is the solicited node address, which I use for the duplicate address detection to make sure that the end of that was not assigned automatically by somebody else. But what's key about this is that router 5 automatically chose its address, which is this one. If I were now to go to the other side, to router 1, and ping this address, so that's what I copied from router 5. It says, I need to know what interface is this on, because each interface has this same network. The key is that anything that starts with FE80, you cannot route it between links. It's only locally significant to the devices that are on that segment. So router 1 basically is going to have this same address multiple times. So it needs to know which interface is it actually on. In this case, it's Fast Ethernet 00.2. This is then my address. No, this is the destination I'm trying to reach. This is my address. So with just this one single command, we're starting the process, actually on, no, yeah, that's right, on this first link. I didn't necessarily have to assign a public address. You just have to turn the process on, and it's automatically going to find all of the neighbors. Now, on the router, we would normally want to go one step further than this, which is to turn routing on, IPv6 unicast routing. Because this is not on by default. Like IP routing is on, but IPv6 routing is not. Then on router 5, I would do the same thing. But before I do that, I'm going to look at debug IPv6 packets and debug IPv6 ND. Then globally, IPv6 unicast routing. Once I turn the routing process on, now router 5 knows not only is it a device running IPv6, it's also a router running IPv6. So it needs to tell the devices, if you want to send packets to some external segment, you can use me, because I'm a router. The source address is coming from the local, the linked local address going to all hosts, FFO2::1. Again, that's the equivalent of the all 255's address. It's telling them things like the maximum transmittable unit, or basically how big your IP packet can be. And it's also going to tell it other things, like what's the network address that you could use for assignment. But typically, we would go one more step further than this, that if the routers are going to route packets, they need more than just the local address. They need a global address. So let's say here on Fast Ethernet 01 that we have an IPv6 address. I could put whatever format that I want here, but it's supposed to start with 2001. That would mean it's a global address. So 2001, and we'll say whatever, A, B, C, D, E, F, 1, 2, 3, 4, 5, 6, :/64. Put a dot there. That should be a colon. And figure out your host address automatically. On router 1, I'm going to do the same thing. So now basically they're in the same subnet. They have the same network assignment, but they're figuring out their end host addresses automatically. On router 5, we would see that we start to receive neighbor advertisements from router 1. This is router 1 telling us what its IPv6 address is, but also what its MAC address is. So essentially, the ARP process is automatic. In the case of IPv4, it's event-driven, where you have to wait till you send a packet before you learn someone's MAC address. With IPv6, you automatically figure out who are all the devices running the protocol on the LAN. And we would see this if we show IPv6 neighbors. That I know this neighbor has this particular MAC address. On router 1, if I were to look at or on router 5, we could see this too. If we said show ARP, if we correlate the output of these two, this MAC address is router 1. So it automatically knows that router 1 has this link local address because we're sending the router advertisements and we're also sending the neighbor advertisements. Okay, so let's look at what's the result of the addresses that they chose. If we show IPv6 interface, it says this is my full address. Some of the digits here are missing though, because the router is going to take any leading zeros and drop them off. So this here, 861, it's really 0861. And this 211, it's automatically 0211. If I were to make another assignment, let's say IPv6 address 2001 0000 0000 0000 0000 00000001/64. When the router looks at this address, if we show IPv6 interface, it's going to collapse it just to this. 2001::1. What this is allowing you to do is just to cut down on the notation. That for all of these sequential zeros, you can take them out by replacing this with 2 colons. But you can only do this once in the address, because otherwise you wouldn't be able to figure out how many zeros did you remove. So the router is automatically going to look at what's the most number of zeros sequentially and then remove those. So a variation on this, if I were to take this address and change it to, let's say somewhere in the middle I put a 1. Then I show IPv6 interface. It's replacing it to this one. So if we compare these, let's say, now the running config is not going to show it either. Let's compare these side by side in Notepad here. This is what the router said it was. This is what I assigned it as. It says this grouping of zeros here is more than this grouping. So it's going to take the greater one and replace this with the double colons. On this side here, we can't drop that 0 because it's not at the beginning. If we drop this one, we don't know exactly where that 1 was placed. We can drop the leading zeros, but not the trailing one. So this means that it's going to be 2001, double colon, then 10, because we dropped the 2 leading zeros here. Then these 4 are replaced by a single 0. These 3 can be dropped. So that's how it's cutting down in the notation. Bitwise, it's still the same value, that it turns out to be this is the long address. Just as much as possible, it tries to cut down the notation so you don't have to keep typing zeros over and over and over. So now let's test this out. On router 5, let's say show IPv6 route. This would be the equivalent of the show IP route, but it's for the version 6 routing table, not for the version 4 routing table. If we do the same thing on router 1, show IPv6 route, it shows me my connected networks, so these Cs, but it also shows you the local addresses that you actually have assigned. A /128, this is the equivalent of a /32 in IPv4. So this is a host route, or the end address. So the network that I'm sharing with router 5 is this one here, the ABCDEF 1, 2, 3, 4, 5, 6. ABCDEF 1, 2, 3, 4, 5, 6. My host address on this network is this one. So So it means that if router 5 were to ping that address, or if it were to telnet to that address, this is router 1. From a telnet's point of view, we don't care that we're going over the IPv6 address, because telnet is an application that's sitting up here that's using TCP for layer 4 transport. I don't care at layer 3 if I use IPv4 or I use IPv6, because telnet is only working above that. It's up to layer 4 to ask layer 3 to do the encapsulation. Then it's up for layer 3 to ask layer 2 what's the MAC addresses. This association here, this is what the ICMP v6 neighbor discovery is doing for us. It's replacing the IPv4 to MAC address mapping, which is the address resolution protocol. So the big thing when you're first learning this is to get over the addressing format. This is what looks kind of scary because it's so long and it's so easy to make a mistake with this. But from beyond that, pretty much everything is going to be the same when you compare version 4 and version 6, where we can do routing protocols. So we can do both static routing or dynamic routing, and there's new counterparts for all of the version 6 protocols. Like RIP version 2 becomes RIP next generation. OSPF version 2 becomes OSPF version 3. EIGRP becomes EIGRP v6. IS to IS and BGP, they actually stay the same. They use the same routing protocol to exchange the IPv6 information. The other key point for this is how do we get the IPv6 packets to go over the IPv4 network? Because as it stands now, the vast majority of the internet does not run IPv6 routing. Most of it still runs IPv4 routing. And there's an interesting site that you can see on this that is, let's see, it is the I want to say that it is this one. It's potaroo.net. If you search for BGP table statistics, you can find this. Basically what this is a graph of the internet's routing table. And this site keeps statistics on what's going on with internet routing. So right now it says this is the growth of the table 1994 to present. This is talking about IPv4 addresses. Whereas you can see from about 2000 on, it's a huge growth in the routing table. This is how many IPv4 routes are being advertised. So right now, it's somewhere around 400,000 routes. This site also keeps some interesting statistics on the growth of IPv6. And there's a comparative report, where right now in IPv4, there's 219,000 prefixes. For IPv6, there's only less than 900 that are advertised to the internet. For IPv6, this is 0.000862% of the total space. IPv4, it's about 40%, but in reality, like 95% of it is allocated. Just certain people don't advertise their space to the internet. Where the number of routes is, actually it's this top one. So just at this point, still the amount of IPv6 compared to IPv4, it's a very, very, very small amount of space. So the problem is that if I have two networks that are running IPv6, how do I actually get them to communicate if I need to go over the internet? Or if I need to go over some service provider that's not running IPv6 routing yet? And this is what tunneling means. A tunnel, in terms of IP routing, or in terms of networking in general, means that you take some sort of data payload, like maybe this is web browsing. And web browsing runs over TCP at layer 4 And maybe we're trying to run IPv6 routing at layer 3, where we look at our application. So this is up at layer 7. So here we have, somewhere we have our layer 5 to 7 protocol data units, or our PDUs. Here we have layer 4 for TCP. Here we have layer 3 for IPv6. Normally we would have our layer 2 encapsulation like Ethernet, and then go over layer 1 like your fiber cable. But the problem we run into is that if the next hop routers are not running IPv6, they're not going to be able to understand this packet when they get it. And I need to make sure that everyone along the path is running IPv6 in order to get my packet to my web server or wherever I'm trying to go. So basically we can come up with a band-aid for this. That if I were to take the full IPv6 packet and its upper layer payload, where the payload is basically what's inside of the IPv6 packet, I'm going to take this and put it inside another layer 3 header. I'm going to put it inside a layer 3 IPv4 header. Then I'll put my normal layer 2 encapsulation on it, like an Ethernet frame. Then when it's sent over the network, the routers in the middle are going to be looking at this and not at this. So I'm essentially hiding from them what's going on inside of the layer 3, which in this case is kind of like layer 3.5, because it's going between what your normal IP packet is and then what's the upper layer protocols. This is kind of similar to what you would think of like an IPsec tunnel, or what's known as an IPsec VPN. That if you wanted to run encryption over the internet, you could do this with the IP security suite, which basically is taking your original IP packet and just putting another IPsec header on top of it, which is used for encryption. So you're taking what was your layer 3 header, and now this is kind of layer 3.5, where this IPsec header is the new layer 3 header. Then it can run over Ethernet or whatever your layer 2 media is. Both of these would represent different types of tunnels, where a tunnel basically means that the devices that are transporting the data, they don't need to know the details of what's inside. So we're adding extra layers of the encapsulation in order to hide this from them. In the case of IPv6, there's a couple different ways that we can do this. One of them is to configure the routers with what's known as a static tunnel. Static tunnel means that I manually define where the traffic is coming from and where the traffic is going to. The two ways that we do this is with what's known as the generic routing encapsulation, or GRE, or an IPv6 IP tunnel, where they basically do the same thing, they're just different ways to accomplish the same problem. There's also some ways to do this automatically. One of them is called a 6-to-4 tunnel, where we take our IPv4 address and embed this into the IPv6 prefix, or the IPv6 address. So basically, based on the packet's destination, the router figures out who is the IPv4 destination it's really going to. And this is one of the common ways to do this over the internet, because we would normally assume that if I'm sending traffic out to the internet, I have to have a unique IPv4 address to begin with. Because otherwise, when I send traffic out, it's not going to be able to get back to me. So we can use this technique and just take your version 4 address, put it into the IPv6 network, and then the router is going to do a conversion between the two. And it's going to take your IPv6 payload, or basically the data that's inside the IPv6 packet, and put a new IPv4 header on top of it. Another way to do this is with what's known as an isotap tunnel. And isotap is a protocol that Microsoft came up with that is the intra-site tunneling protocol. That the idea of this is that you can run IPv6 over your LAN without having all of the devices running IPv6. So this is within the LAN. This is over the WAN. This is the one that the routers run. This is the one that your end host would run. So you'll see that if you go to like your Windows network properties, one of the options you have is to turn on the isotap adapter. Or there's another technique that's kind of similar to this that's known as the Teredo tunnel. And this is what I believe my host has this on, the Teredo tunnel. So one of them is this isotap tunnel. One of them is the Teredo tunnel. But they're basically used to do the same thing. That we're taking the IPv6 packets and then hiding them inside of IPv4 packets, or tunneling them over IPv4. So as you can imagine, there's a lot more details that go into how this stuff works. But just from touching on it from a very high-level point of view, the key is that with IPv6, the change is just at layer 3. So once you learn how the address formatting works, all the other network applications, they're going to stay the same. Then just like the other layer 3 IPv4, the problem that the network needs to solve is routing. As how do I get my packets from one point to the other? And typically you do this with your dynamic routing protocols. Like in a very simple implementation, you could use RIP-NG. That's the replacement for RIP version 2. In a larger design, you might want to run OSPF or EHRP. If you route IPv6 to the internet, you would be using the Border Gateway Protocol, or BGP. Then to deal with the migration scenario, this is what the tunneling is going to solve. And if you want to learn more information about this, which ultimately you're going to have to if you're in IP networking from here on out, one of the best places to start is this book that is called IPv6 Theory, Protocol, and Practice. Now, Cisco does have some of their own publications, like Cisco Press books on IPv6. That's mainly dealing with their specific implementation. But in general, you're probably better off learning the protocol itself first before you learn how Cisco's specific implementation works. So this one is a vendor-independent book. It just talks about what is IPv6 and then what are the different ways that they've come up with to solve some of the problems. It can discover it automatically, and the way that it does that is with the router advertisement and the router solicitation. So when it gets onto the LAN, it sends the router solicitation asking, are there routers? And then the router replies saying, yes, I'm the router, here's the prefix you can use, and then here's the gateway that you could use. The routers actually will do this by default. Cisco's implementation will do this by default. If I were to go to router 2, and who's also on this LAN is what I was configuring before. So it has connectivity to router 1 and to router 5, who are both routing IPv6. If I went to the LAN interface here and said IPv6 address autoconfig, this is what your end host does normally. So Windows and macOS, they do this automatically. If you now look at the show IPv6 interface, we should see that router 2 automatically learned the network that I had defined, 2001 ABCDEF 1, 2, 3, 4, 5, 6, and then it configured its host address based on the MAC address conversion. And then there'll be different options, like it says, I automatically pick this as my default router. So now I should be able to route basic packets out to the network. I don't have any other services enabled, like DNS. I don't know how to reach that. So typically what you do is this is a temporary placeholder until you can get them to talk to the DHCP server. The DHCP server is then going to say, this is your DNS address for IPv6. This is your new global address for IPv6. But the idea is that they tried to make it as plug and play for the end host as possible. That in Windows, you just say, turn IPv6 on. You don't give it any options. And then it automatically figures this stuff out based on the network. So this is the book I was talking about, IPv6 Theory, Protocol, and Practice.